We've calculated the force on a straight piece of wire. That wasn't so bad, IL cross B. We've calculated the force on a curvy wire. Well, we can write the equation for it, but it's nasty vector calculus, so we might not do too curvy of a wire. So let's do one that we can do, where the vector calculus won't be so bad. Let's calculate the magnetic force on a square current loop. Okay, keeping up with all these vectors, all these directions, the cross product, you've got to be fairly careful. Let's go ahead and define a coordinate system. So let's have x that way, let's have y up, and let's have z out. X cross y is z, so it is a right-handed coordinate system. Let's have a magnetic field pointing in the x direction. So uniform B field pointing this way. Okay. And we're actually not going to do a square. Let's do a rectangle. Let's let it have different sides. Rectangular. Just to prove that what we're going to our result will not be dependent on it being a square. And now let's draw our current loop like this. Kind of trying to draw it thick. Too thick. Like that. And since it's a rectangle, this side will be A, have a length A. And this side will have a length B. So nice little rectangle. And current is going to go around this way. Current is flowing counterclockwise in this rectangle. Okay, so here we go. Magnetic force on a current loop. In this case, a nice geometrical current loop. Well, we know that FB is IL cross B. And we know that if it's not a straight line, we have to do an integral, that it's equal to the integral. And in this case, we're doing a line integral around the loop. So it's actually a closed contour integral. We could put a loop on it like that, but it's still I ds cross B. So we can't do this, we have to do this. However, notice that we have made 4 straight sides. So what we're really going to do, as we've done in the past on other kinds of problems, is break this up into 4 integrals. 1 for each straight side. Okay? So let's go ahead and number them. 1, 2, 3, and 4. 4 straight sides. And now let's calculate. Let's break into 4 sides. And let's calculate the force on each one, and then we just have to add it up to get the total force. Okay. So side 1. What is the force going to be? So in this case, this is side 1. ds is basically this length vector going along here. If you add it all up the ds's, it's just this length b, a vector of magnitude b pointing that way. So we know the force is this vector pointing this way crossed with a b field pointing that way. So it's a cross product of 2 anti-parallel vectors. The cross product is 0. If you want to do it with trig, you'd say it's the magnitude of the length times the magnitude of the b field times the current sine theta. Theta between these 2 vectors is 180 degrees. Sine of 180 degrees is 0. So basically, since L cross B equals 0, F1 equals 0. By L, I mean for the whole side. Okay? So no force on this segment. Good. Okay, let's keep going. 2. Segment 2. In segment 2, if you add up all the ds's, or you just think of it as an L, it's a vector of magnitude A pointing down. Okay? And the B field is to the right. So those are perpendicular. That will give you a cross product, 90 degrees. The sine of 90 is 1. So in this case, the force, so here we have that L is perpendicular to B. So this time the force is not going to be 0. It's going to be I times the L magnitude. The L magnitude is just A, the length of the vector, A, times B, times the sine of the angle between them. Well, sine of 90 is 1. And what is the direction? Well, we got to do the right-hand rule. So if we had L cross B, or all the DS's cross B, it would be, I didn't practice this one ahead of time. Let's see, it'd be down along there, curled towards B, it would be out. Right? So it'd be positive Z direction. So it's in the K hat direction. All right? So there is F2, IAB in the K hat direction. So this one actually feels a little force pulling it out. All right? F3. For F3, we have the DS's add up for a length vector going this way, the same direction as the B field. So L cross B is 0 because they are parallel. So F3 is 0. Okay, almost done. 4. F4. Let's see, now again, we have something perpendicular to B. That's good. So it is L, add up all the DS's, basically becomes the vector of magnitude A pointing up. So we know then that L and B are perpendicular to each other. So we are going to have a cross product. That's good. So F4 equals what? I, well, they all have the same I. And it's this side, so it's A. And it's a uniform B, thank goodness. IAB. And now in what direction? Let's see. A cross B is in. So on this one, force 4, this was force 2, force 4 is in. Well, in means in the negative Z direction. So put a negative sign there, K hat. So there we have all of our forces. And if we want the total force on the loop, it's equal to 0 plus 0 is 0 plus, oh my gosh, those are the opposite. IAB minus IAB, so it's 0. So if you have a current loop in a uniform magnetic field, we get no force. So we just calculated the force on a square current loop in a magnetic field, and so the total force is 0. So it shouldn't move. So here, we'll test this with a demo. So this is a square current loop. So if you follow the current flowing from the power supply through this big clip, it goes up through here, out there. There's little cups with mercury in them so that it has electrical contact, but it can still move. Anyway, the current flows eventually through the square and then back out. So nice square current loop once I turn it on. There's no current now. This is a big piece of a magnet, and this is the North Pole, so a magnetic field points out this way. So if I hold this here, this is pretty similar to what we had, where we calculated total force of 0. So let me turn on power supply, and when I throw the switch, we'll have current. So let's see what happens. Total force equals 0. Let's see, and it moved. Well, that can't be. We calculated that the total force would be 0. Let's try one more time. Throw the switch. There it goes again. What is going on? We calculated that the sum of the force should be 0. That's equal to ma. The acceleration should be 0. It was at rest. No acceleration. Why did it move? Well, this, Newton's second law, applies to a point particle, really. Just to an individual mass. It has no degrees of freedom to be deformed or to rotate or anything like that. And what we have here, our square loop, is much more than a point mass. It's a square loop. It can rotate. Right? So what's going on here is that there is a torque. So let's do our simple definition of torque. The tendency of a force to rotate an object about an axis. And I see that as the semester has worn on, I've gone away from my plain spoken definitions. I apologize. A torque means you spin stuff. That's probably what I should have written. So you can have a torque in this case because, as you recall, we have a magnetic field to the right, and we have our square loop like that. And remember, in this case, if the current went around like that, we had a force pulling this way. On this side, a force that way on that side. So what's going to happen is it's going to spin around an axis. And in this case, the axis is right through the center of the loop. So it's going to spin, kind of like in that direction. And that's exactly what it did. The left side came towards me. The right side went away from me, from my perspective. Okay. Now, you got to think about the problem a little bit. Sometimes the rotation axis is defined by the system. In that setup, the little pins are sitting in the cup. It has to rotate about this axis. Sometimes you just have to think about the thing freely floating in space. And you just have to think about the symmetry of the forces that define the axis. But usually in this kind of a problem, the axis around which it rotates will either give it to you or it'll be obvious. So the magnetic field doesn't move the thing. Its center of mass doesn't move. The total sum of the forces is 0, but it can rotate the thing and it can cause a torque. Let's look at this torque in a few more situations. So let's see, before we had the B field to the right, and we had the square sitting like this in the B field. Let's just think, what if we reverse the direction of the current? What if the current went that way? Well, let's see. If we think about it, just go back to the forces. It's IL, the vector L, along the current crossed with a B field. We know up here there's 0 force. I'll write a 0 there because the L vector, the direction of the current, is along the B field. We know down here the force is 0 because it's anti-parallel to the B field, so that cross product is 0. But then down here, L is down, and we cross that with B. Let's see, I didn't practice. L crossed with B is out, so the force is out on this side. And here, L is up. So let's see, L crossed with B in, the force is in on that side. So what you can see is, if you reverse the direction of the current, it's going to spin the other way. Before we had it coming out, here we have it going in, again, from the operator's perspective. So let's turn it on again and have a look. Here's my big magnet. Here's the loop. Before, I made the current go this way, and it came towards me when I pulled the switch towards me. Let's do that again. This is just like before. Pull the switch towards me, and it came one way. Now I'm going to throw the switch the other way. And let's see, throw the switch the other way, and sure enough, it goes the other way. Okay. So that makes sense. Let's check another thing. What if we put the field through the loop? That kind of feels natural. That feels like what you should do. We should have field going through the loop to really make something happen. So let's think for a second. What would happen if we had the magnetic field pointing into the plane of the board, and we had the current loop like this? And we can say the current, again, going that way, like the first example. All right, well, let's see. So if we have the current going this way, then on this section, L is that way. So L crossed with B into the board. The force on this part would be down. I meant to draw this on the outside. So the force on the top section is down. And then here, L is down. So L cross B, oh, the force is in. Take that one away. And then on the bottom section, L is now that way. L cross B, the force is up on that section. And maybe you can see the pattern emerging. Now L is up. For L cross B, the force is in. So here, again, the net force is 0, but this shouldn't create a torque. This is really a compression. The only way that the body will move in this case is if it's highly compressible, if all the square could be shrunk due to the compressive forces. So we really shouldn't expect it to move. So let's see if this works. I'll turn the power supply back on, and I'm going to hold it right here. So the B field is going out and into the square, the loop. We'll see what happens. Sure enough, it doesn't move. Slightly, my fields aren't perfect, but it's not moving nearly as much as before. When we pull down again, you can see it almost wants to contract. Now I'll throw it the other way. Now, if you go through the numbers, it should want to expand. It's not compressible, it won't expand, but we can see that it doesn't really move. See? Very little motion. So everything about the current loop makes sense. Let's think a little bit more carefully about how to describe the torque now. We've seen that a magnetic field causes a torque on a current loop. Now let's calculate how much torque using the real definition of torque. So as you know, mechanics is a prerequisite for this class, and it caused a lot of pain and frustration that I don't review a lot of mechanics. But if you're still here, you probably were pretty good with the mechanics. Well, torque is a difficult concept, often at the end of mechanics, so I want to review it just a little bit. Torque, if we describe it as a vector, it's usually the vector tau, and it's equal to r cross F. Now, let's think about what that really means for a second. The easiest way to see it is to open a door. Do you know how a door works? Here is the door to the demonstration closet that is almost always left open in half the videos. So a door, this big thing, it's on a hinge, and you just push it and it opens. Right? That's how a door works. Right? Let's draw a door and think about where is the torque. Okay? So we're drawing that door looking down. Okay? So here is the door. It's a very impressive 100-year-old door. It's got hinges on this side, probably not the original hinges, but this is the hinge, and that is sort of the pivot point. It swings around that hinge. Okay? It's also got a knob. The knob actually is kind of this two eagles standing around the key or something like that, but we'll just draw the knob. I won't draw the eagles. So the knob kind of looks like that. Okay. So remember, we're looking down. When you approach the door, you reach out with your hand. Right, here's your head, here's your arm and your legs. You're looking down, we're looking down on you, right? And you push. You push on the door with a force. You push with a force F. That's not a torque. You're pushing with a force. You apply a force. Now, what happens is we know that a torque is when you have a force cause something to rotate about an axis. So the other vector we need is r, and that is from the point, from the axis of rotation out to the point where you apply the force. In this case, the line, the place in the door where you apply the force. So that's r. Right? So if you push from really far from the pivot point, then r is really big. If you push really close, r is really small. So tau is r across F. The magnitude is just, we want to get the magnitude of tau. It's just r, that distance times the force, F times sine of theta between them. So if you want to apply the maximum torque, you push at 90 degrees. And that's intuitive, right? You wouldn't go up to a door and to open it, push it like this, all right? You push it straight. You push at 90 degrees to r. If you go pushing at an angle, you get less torque. So this all physically makes sense. The hard part is the direction of the torque, okay? The direction of the torque is not the direction that the thing moves. Let's think about it for a second. It's r across F. So in this case, r is this way, and F is down, right? F is down, r across F. The torque is into the board. Usually we'd draw it over here, actually where the hinge is, and I just happened to draw the hinge as the torque. I made the hinge look like a little vector going in. That's the torque. So when you're making something rotate by applying a torque, the torque vector is actually perpendicular to the circle that it would make. It's normal to the circle. It's not the direction of the force. It's perpendicular to the radius and to the force, and that's the torque.